potentiation. They have LTP, but it's not as strong. The magnitude is less than the animals that also have training but had a poor memory. And the animals that had a poor memory are no different than the control animals that didn't have any memory. That's shown by the bar graphs on the right. So that's quite remarkable. We can demonstrate that the animals formed the memory. It persisted for up to a month, and if and only if it did, you could measure a detectable change in the synaptic strength and synaptic ability to change in this part of the brain. There are very few changes that have ever been described like that. In fact, there are other changes that you could detect in the synapse. What's shown here on the x-axis is the strength of the synaptic response, and what's shown on the y-axis is the likelihood that that response is associated with the generation of an action potential, what we call a spike. So because the red trace is shifted to the left, what that shows is that for a particular stimulation, or response to a stimulation, you get a bigger or more likely generation of an action potential. So this circuit has become more responsive, if you will, as a function of this training. You can see in the upper trace here that this is a repeat of what I showed you before. The high-frequency stimulation causes long-term potentiation, but it's of a lower magnitude in the trained animals than the untrained animals. The synapses are harder to change after the training. In fact, that's not quite true. If you look at the lower trace, this is a different kind of stimulation. This 1 hertz, 1 time for 15 minutes stimulation. This causes a depression of the synapse, a weakening of the synapse. And the trained animals, instead of having a weaker depression, have an enhanced depression. So the synapse changes its plastic properties. It's harder to strengthen, easier to depress, easier to weaken. And this again is after just a few minutes of training across a few days. So has the brain saturated in its ability to change its synapses and therefore store memory? Well, this trace shows you that's not the case. If we repeat the high-frequency stimulation after, say, 15 minutes, we can see that the trained animals potentiate eventually just as much as the untrained animals. So it's not like the brain has full up, if you will, in its ability to make plastic changes. It's just now different. Again, this is different not because of a drug, not because of any electrical stimulation, just because of the animal's cognitive experience, which in these cases correspond to about 30 minutes of experience during training. So with 30 minutes and 120 minutes, 2 hours, you see the possibilities. So we can look in some detail at the neural circuit here. So let's talk about the CA1 neuron, what's shown here in red. The VHC is the ventral hippocampal commissure. It's an input from another portion of the hippocampus on the other side. The CA3 region is the hippocampus input to CA1, and it arrives at this functional part of the ventral hippocampus. PT stands for perforant path, and that's an anatomical term for the input from the neocortex, from the entorhinal cortex, that can arrive both in the dentate gyrus as well as in the distal dendrites of CA1 called the lacunosum folliculare. So we're going to look at the response to perforant path input in CA1 as well as the response to the ventral hippocampal input in the proximal dendrites of CA1 and how cognitive training changes that. And so in order to do this in an awake animal, or at least an intact animal, these data that I'll show you are from an animal that's been trained and after training anesthetized, so we can be sure about where the electrodes are. What we're going to do is to put 16 electrodes along the somatodendritic axis of the brain in order to be sure about where it is that we're reporting from one animal to the next, and we're going to, in this way, triangulate and focus our attention on the particular electrodes that are in the particular compartment that we want to study. So when we do that, we can calculate many things. What I'm showing you here is something we call So if we look at the ventral hippocampal responses in the untrained and the trained animals, just looking at the colors there, you can see that there's a difference. The trained animals have a difference in their sources and sinks. They appear in the same places anatomically, just their intensity is substantially different. And if you look in the perforant path, the trained animals, this is the same sets of neurons, the same electrodes, but a different input. And you can see that in the trained animals, while the locations of the sources and sinks are approximately the same, the intensity is actually not increased, it's decreased. So this is rather remarkable. It's sub-region specific alterations in the synaptic responses both in excitation and inhibition within this narrow region of the brain. And those data are summarized, shown below, while the upper case is an individual. What I can show you is quantifying that in the lower bar graphs there. You can see that the trained animals have a much bigger source, bigger inhibition, as well as excitation with the same. In the ventral hippocampal case, which is the CA3 region of the hippocampus projecting to the red area that's indicated red in the cartoon, which is the proximal part of CA1, and the area indicated in blue, the perfractative input, you get rather the opposite change. Again, that's quite remarkable. Remember, this is training, and in this case, the training was actually just, again, across a single day for 10 minutes of trial and retrial. 30 minutes of activity was sufficient to change the functional characteristics of this part of the memory circuit. So what I've shown you so far is that experience can persistently change neural circuit function. The changes that I showed you before were measured at least 24 hours after the training, and they persist in other experiments that we've done for at least 50 days. So that begs the question, could we actually use cognitive training directed in one way or another to tune the neural circuitry function so that we can be preemptive in preventing cognitive dysfunctions that will arise later in life? So we decided to ask this question some years ago. Could preemptive cognitive training prevent future cognitive impairments? So we had to arrange to have future cognitive impairments. And what we did was we used a neurodevelopmental model of a mental illness, potentially schizophrenia, and to do that, because we wanted it under our experimental control, what we did was we took neonatal rats when they were 7 days old. This corresponds in terms of brain development to a time that's approximately like the third trimester of a human pregnancy. And what we did was we damaged a part of the brain called the ventral hippocampus. This is a portion of the brain that, as it develops right around this time, is developing its connections to the frontal cortex, and it changes a number of things in the brain that have at least superficial resemblance to the kinds of changes that we believe happen in schizophrenia. Hence, we'll call it a schizophrenia model. And so what we did was we damaged this part of the brain, and what we could test is the animal's ability to do this cognitive task when it was an adult at about 60 days old. And 60 days of age corresponds to young adulthood. You can imagine that as 18, 19, 20-ish in human terms. And so when we ask the animals to do this kind of a task, I'm showing you, in this case, the same place avoidance task that we've used before. From this perspective, it should be apparent that the place to avoid, that the rat is doing the job of avoiding, is fixed in the room using stationary cues, but you can see the feces on the arena. They are rotating, and they rotate through the shock zone sometimes, and sometimes they're away from the shock zone. That should give you the impression or indication that using local cues on the rotating surface are not useful for identifying the location of shock. And when animals are trained in this particular task, if they are the schizophrenia-treated or schizophrenia models where they have the neonatal lesion, they're impaired. They make many more errors than the control animals who simply had the injections made of the vehicle solution rather than the toxin that we injected. Okay, so now we have a cognitive output or assay for the debilitating consequences of this in our early lesion. What we found that was interesting is this debilitating response only occurs in the presence of the distraction. And what we've done here is we've used the identical task, but instead we put a 2-centimeter layer of water on the arena. And what that does is it dissolves and dissipates all of the local olfactory cues that the rat was using that it had to actively ignore because they were irrelevant for localizing where the shock was in the red shock zone here. And when we do that, when we test the animals as adults, despite having this lesion, they clearly are okay. So their memory is all right. They don't have a memory deficit. What they have is a deficit when they are challenged to use one kind of information and ignore another kind of information. And that's the kind of deficit that we see in mental illness like schizophrenia. So here's the interesting thing. Early in brain development, and as you go through puberty and such, the brain has a state that we say is hyperplastic. It's more willing to change. And so we took advantage of this knowledge, and during adolescence, when the rats were 35 days old, which corresponds to being something like 13 in human terms, in terms of brain development, what we decided to do was to give them this cognitive training to use one kind of information and practice in ignoring the distraction, as I showed you before. And the control animals simply were put on the arena, the shock was never turned off. So they have the same physical experience of the arena, they just didn't have the few seconds when the shock was turned on. And by the way, the shock is only turned on for half a second. And if an animal receives 10-ish shocks during a trial, the trial is 10 minutes, but the shock is only on for about 5 seconds. So otherwise, the environment is really identical, and the experience is identical between these two groups of animals. And so what you can see is, not surprisingly, we understood this during adolescence, the schizophrenia model animals are just as good as the control animals in learning this task. Here's the surprising thing. What we wanted to do is we controlled for the animals who had the non-cognitive training just walking around the task,